Thank you, and good afternoon. As Maria and others mentioned earlier in the session, we're within months of the launch of the first set of commercial lunar payload services landers from NASA. One of those first launches will be with Intuitive Machines. Ben Bussey will be talking a little bit more later in the session. This is an artist's concept of IM-1, including a payload that we're flying to do the first astrophysics and radio science from the moon, first NASA radio telescope on the moon. You can see two of the monopole antennas here of the four that we will be flying as part of a payload called ROLSES. ROLSES stands for radio wave observations at the lunar surface of the photoelectron sheath. So we're going to be probing for the first time the plasma that lies near the surface of the moon. It's been speculated to exist for a long time, but has not been detected. Our radio antennas are simple stator antennas. They are hollow tube antennas that are spring-loaded that will pop open. This is the actual flight models of the antennas shown in the center here. And then the brains of our instrument is a digital radio spectrometer. You see the flight board here as well. It's FPGA driven. The instrument was built at NASA Goddard Space Flight Center. We were one of the very first instruments selected for the first round of CLIPS missions. Nat Gopalswamy is the PI. Bob McDowell was the previous PI. Bill Farrell and myself are two of the lead scientists. This is a new build, but it has heritage from NASA's SMAP mission. The radio spectrometer has two bands, goes from a low band, where we'll be doing the plasma observations, to an upper band for more sky observations ranging from 2 kilohertz up to 30 megahertz. And as I mentioned before, we'll be flying on Intuitive Machines 1 Nova-C lander. Here are some more details on the instrument parameters and some pictures on the right-hand side, relatively recent pictures of the integration of payloads onto the panels that go onto the side of the lander, including, once again, one of our stator antennas that you see here at the bottom. Our landing site, NASA requested that we look at landing at the near the south pole of the moon, and the landing site that was selected is called Malaparte A. It's on the rim, on the other side of the rim of this small crater. It's about 10 degrees away from Shackleton and the South Pole. Looks like a pretty good landing site overall. So what does the radio sky look like from the moon? That was an interesting question that hadn't really been tackled before. So we did some simulations that you see here of what the radio sky at about 10 megahertz, 30 megahertz in this particular case will look like. The X at the center here is the zenith. So imagine that you project this onto a planetarium dome. This X is what you will see in the center. Let me run this one more time. And you can also see the Earth here and Jupiter. The Earth moves right around the horizon, and you can also see the sun. This is for a time period in late August, early September. You can see the dates located over here and the what we expect to see from the sky. Obviously, we don't have this kind of resolution, but we'll have a spectral capability. Our science goals, the electron sheath, as I mentioned before. Also, we'll be looking to detect solar, planetary, and other radio emissions. We'll be doing the galaxy spectrum at less than 30 megahertz, which is poorly constrained at the present time, and a few other additional environmental issues. So first and foremost is we'll be looking at the photoelectron sheath. Here are some models of that sheath from Poppy and Harani. This is density versus height, and this depends critically upon the state of the solar wind at that particular time, as you can see here. And different models from different groups have densities that vary by as much as a factor of 10. How do we measure the density? Well, we will be actually measuring the plasma electron frequency, and that is measured, basically it produces a cutoff in the spectrum when we hit the plasma frequency. It's estimated to be around 60 or so kilohertz, and that electron frequency is directly proportional to the square root of the density. So that's how we will go about measuring it. In addition, this is what we expect our sky data to look like. This is actual data from the NASA wind waves experiment. This is a dynamic spectrum, frequency on the y-axis versus time on the x-axis. And what you can see is the richness of the low frequency spectrum. There's radio frequency interference coming from the Earth, the horizontal lines, Jovian bursts, solar type 2 and type 3 bursts. And below a megahertz, the Earth is a powerful source of radiation called the auroral kilometric radiation. It's a maser cyclotron emission. One of the things that we're going to be looking at here is we're really looking at the Earth as a prototype exoplanet. The magnetospheric emission in principle can be detected also from nearby exoplanets using a low frequency array on the far side. So we'll be looking at the Earth as a prototype of some of that exoplanet emission in the future. In addition, we'll, since the Earth is in view, we'll be looking at terrestrial RFI. That hasn't been measured in a number of decades now. This is also wind waves data that we're looking at here. This was when the spacecraft was near the moon in 1999, and you can see these very broad bands of terrestrial transmissions, RFI. We'll be looking to see how strong that is, how variable it is, as to whether or not a low frequency array on the near side can be used for studying solar bursts in the future, but also looking at these terrestrial RFI once again in terms of exoplanets and emission from a potentially intelligent civilization associated with an exoplanet. Also, dust is one of the goals. As many of you know, both Surveyor 5 and also Apollo saw a horizon glow on the moon that some have interpreted as scattered light from electrostatically elevated dust. Our radio antennas are actually pretty good dust detectors, as was illustrated by during the Cassini mission, when dust from Saturn's F ring, shown here on the right-hand side. This is a voltage spike that occurs when the charged dust strikes the antenna. This will be challenging observations, but Bill Farrell is taking the lead. We will make observations, particularly at sunset. We have about 8 hours of battery life after sunset. So we'll be looking at that transition. Another goal is to begin measuring the dielectric properties of the subsurface. The reason is that our antenna beam couples electromagnetically with the subsurface, and this is an issue for cosmology observations that we'll be undertaking in the far side with a subsequent mission. This illustrates some of that coupling in a modeling sense. This is power in the far field versus angle. So theta 0 is looking at the zenith, and 90 degrees is at the horizon. You can see that these models of the antenna in a vacuum are relatively flat versus on a layered regolith, including also the lander in this case. You can see how that is, this is altered. So we've been doing specific modeling now to look at how well we might be able to constrain the subsurface dielectric constant using Jupiter as a passive source. And what you're seeing here are model residuals from each of the 4 monopole antennas. Looking at the table over here, you see our chi-squared and our probability such that the input model was epsilon of 5, and we're able to constrain that relatively well in this first observation. So we will be attempting to do that once again in preparation for understanding that coupling for cosmology observations. Lastly, just a couple of pictures. This is taken when I had a chance to visit Intuitive Machines last year. So you see a full-scale model of the lander over on the left-hand side. And then on the right, I'm standing next to my colleague, Susan Lederer for NASA Johnson in the NOVA Control Center, very nicely built by Intuitive Machines. Our launch is going to be in the third quarter, so the next couple of months is what we are expected. This will be followed a few years later by an instrument called Lucy Knight that my colleague Andrei Slozar will be talking about next. And this will be a cosmology mission to operate on the far side of the moon. We're hoping what we learned from ROLSES will feed into Lucy Knight. In conclusion, then, just want to say that the CLIPS program is a high-risk, high-reward program, but is potentially a real game changer in terms of regular access to the lunar surface, allowing us to fly payloads, reconfigure them, fly them again. ROLSES will be the first, followed by Lucy Knight, and then subsequently, we believe these are preparing the way for future arrays of low-frequency radio antennas on the lunar surface, possibly in conjunction with Artemis astronauts, and particularly on the far side of the moon. So with that, I will stop there